design, and this will be as per the limit state that we'll be discussing. Now, this is one among the first limit states in the limit state method of design. This is one among the first strength-based design methods, which is for flexural design. So, agar usme, now you have limit state of collapse. So, limit state of collapse would be now in it would be have in different stress patterns. It could be for compression, it could be for tension, that you could have limit states. And similarly, you could be having these for shear and torsion. So flexure is a part of the stress patterns, जिसके लिए हम limit state of collapse we can consider to be determined. Now, but it's not a material property that you directly get for all the materials. For example, you might get the flexural stresses for concrete, but it still is not pure compression, neither is it is pure tension. It's a combination of both the two states. For example, if you have a beam, in a beam you would be, if it's under flexural, flexure means it's under bending. Under flexure, this beam would undergo tension towards the bottom side and compression towards the top side. So it's not under pure compression, neither under pure tension. So flexure becomes a very good property to study first, because it shows parts of compression, parts of tensile behavior, and it will also show, to accompany this, there will always be shear in this beam. So you can also study the shear at the same time. So that's why we start with beam designs, because they give you an idea about all the three: compression, tension, and shear, which are the predominant ones. And for serviceability conditions, for the limit state of serviceability, it also shows the deflection profile. So beams are the first elements that we usually study in flexural design. The reason being that it's showing behavior in all the different stresses, in compression, tension, shear, as well as for serviceability, the deflection parameters. And it can also tell you about the cracking patterns on the tensile side, which will occur first. You could the failure always would not always, it would be mostly towards the tensile side, because concrete is poor in tension. So the failure will be towards tensile side. So you can visualize the cracking patterns towards the tension side, जो कि bottom side है एक beam का. तो flexural design for flexural stresses, so you would have flexural stresses or bending stresses. Now, these flexural stresses or bending stresses, what are they? They are stresses that are acting onto the, these are stresses that are acting on the structural element. Here, the structural element is a beam. तो उस पे act कर रहे हैं. How do they act? They act once the flexural forces are applied onto the. Now, what is a flexural force? It's a bending force that is being applied onto the beam. So this flexural, under the action of a flexural stress, it will undergo flexural strains or bending strains. So you would have a stress strain profile always. Under every stress, there will be a corresponding strain. So you will always have a stress strain profile development for each of the elements. Now we know that we are studying reinforced concrete design. And in reinforced concrete, it's not only concrete, it is steel as well. So till now we have studied the design philosophies, and we concluded on limit state method of design, जहाँ पर हमने ये conclude किया that there are two limit states: limit state of collapse and limit state of serviceability. And most of the design philosophies now, since year 2000 once we moved into the new millennium, are being done as per the limit state method of design, जिसमें हम limit state of collapse as well as limit state of serviceability, both are being, that means strength as well as its long-term durability properties are being taken into account. So once now that is clear to us, that we have the design philosophy clear to us, so it's very important now to know that how do the two materials, that is steel and concrete, they behave together. I just briefly described to you last time that there is a, once we were concluding the class, I described to you the strain compatibility between steel and concrete. So I'll first of all take up a beam section. This is a section of a beam which will be under flexure or under bending. So this beam section I have shown here, there are these red will be the steel at the bottom. Now, why did I provide the steel at the bottom? Because steel, now this beam I just described to you, it's in compression at the top and in tension at the bottom. क्योंकि ये compression है towards the top side, concrete is good in compression, so no requirement of additional strength taking on the compression side, because concrete may take all of that itself. But on the tension side, it has got a weakness. Concrete has got a weakness towards the bottom now. So we require some material which will take up the tensile load. For that, we are providing the steel here. So these steel bars are being provided. इनका purpose क्या है? The purpose is now to take the tensile stresses. So I have roughly assumed right now that in this beam, there is only tensile steel. So I will call these steel bars, which are at the bottom, I will call them as tensile steel. And there is rest of this all is ye jo baki, you have this, let me mark it gray. So this is all concrete. This is all concrete. Rest of it is concrete, including on the compression side. Now, how do you demarcate कहाँ तक compression हो रहा है और कहाँ से नीचे फिर tensile stresses are predominant onto this beam section? ये आपको clear हो रहा है that everybody of you, that how is compression acting at the top and tension at the bottom? Anyone who has any doubt on this? इसमें compression कैसे develop हो रहा है at the top and tension at the bottom? Nobody has a doubt? You are clear that there is a compression at the top and a tension at the bottom. Now the question is, if the top portion, this one, up till some point, I'm not telling you the point, there is some point, let me make a line. Up till this line, there is compression acting here. So there is compression acting till a line, and I don't know where the line presently is. And then below it, there are tensile forces or tensile stresses acting on this beam. So there is a portion of the beam in which there is compression, and there is a portion of the beam in which there is tension happening. Now, this depth, up till which it's in compression, you can call it as XU and designate it by XU, and we call it as neutral axis depth. So this axis at the center is the neutral axis. This is the neutral axis. तो ये line जो बीच में है, there is zero tension, zero compression here. तो सबसे ज्यादा कंप्रेशन कहां पर एक्ट करेगा? The maximum compression will be acting here at the top. So where will be the maximum tension happening? It will be at the bottom. क्यों? Because this is the extreme fibers. These are the extreme fibers. अगर आप किसी चीज को खींच रहे हो, bend कर रहे हो, the topmost fiber will be compressed the most, and the bottommost fiber will be under tension the most. वो सबसे ज्यादा खींच रहा है और ये सबसे ज्यादा कंप्रेशन में आ रहा है at the top. तो बीच वाली एक लेयर है जहां पर न्यूट्रल एक्सिस है, देयर इज नाइदर कंप्रेशन नाइदर एनी टेंशन हैपनिंग एट दैट लेयर. सो this layer, the neutral axis layer, has got zero compression, zero tension. So the depth from the top extreme fiber, from the compression extreme fiber, this is the extreme fiber here, extreme fiber, at the top, which is in compression, and there will be a extreme bottom fiber which is in tension, again extreme fiber in tension. So this layer at the center now is the neutral axis, and the depth from the topmost compression fiber to this is the neutral axis depth. Very important, you need to know the neutral axis depth for determining the property of the every property of the flexural property, the compression properties, and the other properties. You need to know the neutral axis depth. So your design will be actually dictated by the depth of the neutral axis. So this XU so becomes very important in your design. Now let me tell you about how the stresses actually develop in the steel. I have already discussed this last time. There is a stress strain diagram for steel. For example, this is your steel, and there is a point where it's 0.0035 strain, and I told you that there is a point where it's 0.002. Sorry, this is concrete, 0.002 and 0.0035. Let me make for the steel. So for concrete, you would have, so for steel, it would be somewhat like this. This would be 0.02 and it is 0.002 at a particular location. I told you this last time. So there is a strain compatibility up till the point 0.002. I discussed this last time. Now, whenever there will be flexural forces occurring onto the stresses acting onto this beam, the stress strain profile would be somewhat like this. If this is the neutral axis now, ये आपका stress profile. If I first make up the stress envelope for this beam, सबसे ज्यादा stress कहां पर develop होगा? At the top, and सबसे it will go towards zero at this point, and then it will again go to in tension. Now in tension, only for concrete first, and there is no steel here. Let it be stress profile only for concrete. Concrete stress profile. Concrete can take stresses in compression to a lot of extent, and in tension it can take to very less amount. So that's why I made, there is more towards compression side and less towards tension side, the stresses that it can take. लेकिन जब यहाँ पर एक्सट्रीम फाइबर पे आपका मैक्सिमम let the stress here be sigma y, not y, let it be sigma 1 right now. Sigma 1 is the stress in concrete in compression at a particular point. अगर मैं इसको एक्सटेंड करता हूं टेंसाइल बिहेवियर को, so there will be a point where this is sigma naught in tension, so this is sigma 1 in compression. So this sigma naught t would be reflected by similar triangles on the compression side as well. तो पहले कंक्रीट किस में फेल हो रहा है, टेंशन में या कंप्रेशन में? Yes, any one of you? In which पहले किस में फेल हो रहा है? What is the stress pattern जिसमें ये पहले फेल होगा?
Tension.
In tension. So towards the bottom extreme fiber, it will fail first. So there is a point after this. Right now I have assumed the behavior of this concrete is linear, but it's not linear. You know, this is the behavior of concrete. It's linear up to a certain point. उसके बाद ये non-linear चला जाता है. So that's why मैंने यहाँ पर एक straight line draw की है. Otherwise, its behavior being non-linear, every point would be in a different. So this is a point sigma naught t. अभी ये fail नहीं हुआ है. It's still in the linear phase. Let there be another point जहां पर ये अब fail हो रहा है. And this point, let this be sigma u in t. मैंने as u designate क्यों किया? It's the ultimate tensile failure point in of concrete in tension. तो उस टाइम पे its behavior would be not straight line, it will be somewhat like this. जैसे कि concrete का stress strain profile आता है, वैसे ही इसका stress diagram, it would be resembling that. This is the ultimate failure point. और जो आपका ये point है, because this is a point which is in point ut, and this will follow the stress pattern at that point. It will follow the stress pattern of the concrete at that point. Now, similarly, now it still has not gone into the compression zone. अगर मैं इस point को extend करता हूं, it will reach to this point. So you can resemble this point here, ये वाला point. What is this point now? It's resembling sigma ut. So the failure is happening first in tension, even before the compression point has even reached the linear point. तो अभी linear yielding point भी compression में नहीं आया है for the concrete. So next you would have this is the compression side. There will be a point when it will reach to the yielding point, the failure point, sorry, u in compression. But now this graph will not be linear, it will be this will be following the non-linear pattern. तो पहले आपका टेंसाइल फेलियर हो जाता है फॉर कॉन्क्रीट इन tension side. So that will happen first. If you take it as similar triangles, you can see that it's happening first. Then you will get the linear point for under compression, which is the yielding, or below that the elastic point. And then you will have the final failure. At the failure point, you always have the graph resembling somewhat like this, because it's now in the non-linear phase, the plastic phase. So different points are in different plasticities. Now there is a certain layer from here up till here, even when it's in the compression failure up till this point, जो कि अभी linear portion में ही है. So there will still be certain portion which will be in the linear phase, which will be still in the elastic phase for concrete. So this is the neutral axis depth that you have for concrete. Now, what is the stress, the ultimate stress for in concrete for compression? Did we discuss this? Ultimate stress कितना होता है in compression for concrete? हाँ जी, we have already discussed this. What do we take as the ultimate stress in compression? As ultimate stress here, this sigma UC, जहां पर compression में ये fail हो जाएगा, that point will be FCK in compression. क्योंकि हम compression में ही concrete को test करते हैं under CTM, compression testing machine. We do not test it in tension usually. So we hardly know this property, sigma UT. हमें नहीं चाहिए. We don't even require this property. Why we don't require this, I will tell you later. तो हमें कौन सी प्रॉपर्टी चाहिए कंक्रीट की? We need the property in compression, this sigma UC. तो वो हम CTM पे निकालते हैं. We know that property now. और उसका वैल्यू क्या है? FCK. It would have been FCK. Sigma UC would have been FCK for ultimate stress. But there are conditions to this. Number one, there is uncertainty that we discussed. There are various uncertainties in the loading and in workmanship and other things. So there is uncertainty regarding that. And then we usually determine FCK for the cube sample. While as from the shape factor, if you check for a cylinder sample, cylinder में जो you would be having greater you could get greater amount of strength from there. So, but lesser strength there, because cylinder has got one dimension quite larger than the other. So cylinder is somewhat like this. So it has got a shape factor. So that's why the cylinder comes to have lesser strength, because it slightly buckles as well at the same time. So it's and the compression here in the cylinder is not as the aspect ratio has got a effect on that. The aspect ratio between this height with respect to this width, जो कि cube में नहीं है. Cube has got aspect ratio of 1. Cylinder में it has got an aspect ratio of around 2. तो उसमें you have lesser strength there. So cylinder में shape factor plays a role. तो ये दोनों चीजें, uncertainty and the shape factor, जो कि cylinder में कम strength आ रही है, that needs to be incorporated in the design as well for flexure. तो क्या करते हैं? We have the shape factor and this taken into account by incorporating two factors, two coefficients for FCK. So now your sigma CU would be first taking into account the shape uncertainty. So we take it 0.85 FCK. This is the first. Then we also take into account the slender shape factor, so that makes it 0.80. तो इसका 20% लेते हैं कम, and for uncertainty we take 15% less. So if you multiply these two, 0.85 into 0.8 into FCK, there are two coefficients now here. तो ये बनता है 0.68. So we usually take it as 0.677. आता है ये value 0.677 FCK. So this would be your design. This would be your compressive strength, the ultimate compressive strength at failure. This value, इसका value ये होगा, sigma UC का value आपका 0.677 FCK है. Otherwise it would have been FCK itself, जो कि मैं अभी कह रहा था. It would have been FCK, but we also take into account the shape factor and the uncertainty, so we keep it lesser value. The value of the compression strength, if we are keeping it lesser than what it actually is, उसका ये मतलब है, because we are designing it, so for design purposes we are incorporating both uncertainty. We do not want it to cross this value now, 0.677 FCK. So now there is one more thing, which is the material partial safety factor. And for concrete, we already studied last time. I told you the material partial safety factor is how much? 1.15. Sorry, 1.5. For steel, it's 1.15. So we resemble it by gamma M. Gamma M is the material partial safety factor. For concrete, it would be gamma MC. So gamma MC for concrete is 1.5. So keeping that into account, you now have two curves that would develop. Let me make another figure. This is one curve for concrete. And this is the characteristic curve. We call it by characteristic curve. What is characteristic curve? Which has FCK in it, but now it also has the effects of uncertainty and shape factor taken into account. So this value here, यहाँ पर, this value is 0.677 FCK for a characteristic curve. So this is a stress strain graph for concrete, जिसमें हमने दोनों चीजें incorporate की, uncertainty and shape factor. The ultimate stress point is 0.677 FCK. लेकिन जो ही हम इसमें material safety factor लेते हैं, what happens is that this sigma U, जो कि एक final point था, sigma UC, that will be divided by gamma MC, which is the partial safety factor, जिसका value आपका है 1.5. So sigma UC is 0.677 FCK. If that is divided by 1.5, the value that you get is 0.45, but we usually get it as 0.447 FCK, somewhere near this range, 0.447 FCK. So there will be another curve, जो कि डिजाइन कर्व होगा इसका. So this curve below this characteristic curve will be the design curve for concrete. So ये design curve, it has, you have already incorporated the partial safety factor for the material here 1.5. तो इसका वैल्यू उससे भी कम आ रहा है. So you actually are designing for this curve, not even for this, taking into uncertainty and shear factor. Now you're also taking in the safety factor for the material. So overall आप कितनी strength utilize कर रहे हो? Only this much, 44.7% of FCK. That's the ultimate strength that you are utilizing for design purposes. तो finally इसका value आपका ये sigma u compression for design purposes, its value is just 0.447 FCK for concrete. हम concrete की बात कर रहे हैं अभी. Its value is 0.447 FCK. What is this? This is the stress in compression for design purposes. हम कितना लेते हैं? We take it only as 0.447 FCK. Now, your concrete should have stress less than 0.447 FCK. In flexure, जब ये flexure में होगा, its failure is still happening in tension first. तो लेकिन हम इसको डिजाइन कर रहे हैं for compression only. तो tension के लिए क्या कर रहे हैं? This is the compression failure, लेकिन इसका failure तो पहले tension में हो चुका होगा. So इसकी तो नौबत ही नहीं आएगी कि ये कंप्रेशन में फेल हो जाए. ये तो पहले ही टेंशन में फेल हो जाएगा. So what do we do? Which we assumed first, that will provide the steel bars at the bottom of this beam or this flexural member. तो वो steel bars क्या act करेंगे? They will act here as tensile members somewhere here. There will be a steel bar and they will be acting as tensile members at this location. And there they will have a separate tensile stress strain profile under tension. तो इसका tension graph कैसे होगा? I am showing you by an arrow. ये एक point है within this whole structure. This is your concrete in compression now at the failure point. The graph is like this, the stress strain graph for concrete. ये neutral axis है. So this is compression. C, हम इसको positive भी लेते हैं. और ये point आपका 0.447 FCK आ गया. Now there is a point on the tensile side जहां पर steel है. There is steel bars are there here, somewhere here. Just above the extreme fiber हम steel bars देते हैं. We do not provide them. सबसे ज्यादा extreme fiber tension में कौन है? ये this point. But we still do not provide it at the extreme fiber because we need a cover for steel. Otherwise corrosion of steel will happen. So we provide cover at the bottom such that steel is hidden within the concrete. So just above it, cover देकर, there is steel bar, and this steel bar will now be under tensile force P, which will be negative. The stresses, these are the stresses. This is stress in concrete in compression is 0.447 FCK. Now the stress here for steel would be sigma S. We usually do not go towards ultimate point. We go for yielding point for steel. the point at which it is yielding. Now, if you have a look at the stress strain graph of steel, you will see that there is a yielding point somewhere here. So वहां पर you will have the stress, the maximum stress as sigma sy, but this is the again the characteristic curve of our steel. There is no problem in terms of steel कि वहां पर shape factor है, because steel is manufactured in factories. So there are hardly any issues with the shape factor. There is hardly any issue with the workmanship. Steel bars एक ही size के होते हैं, length के होते हैं, so no issues with the shape factor, no issues with the uncertainty dealing with workmanship. So we do not incorporate that factor here for steel, but we have to incorporate the जो इसकी material property है as partial safety है. So design curve will be below this. The design curve will be below this for steel. और उसका value क्या होगा? What is the partial safety factor for steel that we took? Yes, any one of you?
1.15.
Yes. So this will be sigma s y divided by 1.15. तो ये value कितना आएगा? It comes to be 1 divided by 1.15 आता है आपका 0.869. That's 0.87. Now sigma sy, or you can call it as fy. By both terms we designated sigma sy or by fy. So you can also designate it as 0.87 fy. Sy here is, this was, ये confusion create करेगा between this and this. Let me call this as fy here as well. So this is fy by 1.15. So that's 0.87 fy. So sigma sy, which is the stress now developing in the steel at its yielding point, is 0.87 fy. This is for concrete in compression. जब वो fail हो रहा है, it's the stress in the extreme fiber is 0.447 fck. At the same time, for steel, it's 0.87 fy. So these are the stresses in steel and concrete in flexure that will develop in these materials. पहले कौन develop होगा? पहले concrete अब fail होगा कि अब पहले steel fail होगा? Now that is decided on what we call as balanced design approach. पहले कौन fail होगा? It's decided by the balanced design approach. Now, what is a balanced design approach? If there was no steel in here, it would be all concrete. पहले कौन fail होता? पहले concrete ही fail होता. कैसे fail होता? In tension fail हो जाता. हमने steel क्यों डाला? Such that the concrete does not fail in the tension. So steel will take the tensile loads towards the tension side. तो हम क्या consider करते हैं? इससे पहले मैंने जब ये ग्राफ बनाया, I showed you there is a tensile stress pattern in the concrete as well. जब मैंने steel डाल दिया इसमें, I no longer showed you the tensile stress in concrete, because it hardly now matters कि यहाँ पर concrete है कि नहीं है, because all the load in the tension side is now being taken by steel, and that taken by concrete is negligible as compared to steel. the Fy for steel would be easily 415 500 megapascals, और concrete का तो 2 megapascals है in tension. So this is negligible. The role of concrete in taking the tensile load is almost negligible. So for tension side, we say we do not take the stress envelope once the steel is taken here. तो हम स्टील का ही एनवलप लेते हैं. तो इनको आपस में अब कंपेयर करते हैं. तो बैलेंस डिजाइन अप्रोच क्या है? व्हाट इज बैलेंस डिजाइन अप्रोच? बैलेंस डिजाइन अप्रोच ये है कि क्या पहले अब स्टील फेल होना चाहिए और कंक्रीट फेल होना चाहिए. बैलेंस डिजाइन अप्रोच से कि दोनों इकट्ठे फेल होने चाहिए. मतलब उसका ये मतलब है जो टेंशन साइड में आपके स्टील के बार्स है, द टेंशन in the taken by the steel here, this is taken by steel, should be equal to the compression taken by concrete. This is the balance design approach. So what is T? T is the tensile force. C is the compressive force. What are these? These are stresses. अब if you have steel जिसका area of cross section AST है, AST क्या है? Area of cross section of steel bar. ये जो steel bars है इन सब का मिला के on the tension side area of cross section AST है. AST क्या होगा? What will be the AST for these three bars? It will be pi by 4 into d square, which is the area. अगर ये 3 बार से तीनों बारों का फिर for 3 bars, so that will be the total area of cross section of the 3 bars which are under tension. ये जो section काट रहा है तो इन तीनों का diameter से निकलता है. D is it the diameter of the each of the bars. Then you get the area of cross section of each of these bars, steel bars. वो आपको total मिला के AST मिल रहा है. Because these 3 bars, इनका cross section, this cross section, वही resist कर रहा है the tensile forces. The cross section, the dia of these bars is resisting the tensile forces in flexure. क्यों? क्योंकि अगर आपके पास एक beam है and this is the steel bar in the beam, इस पे load ऐसे आ रहा है. So what will take the load? It will be the cross sectional dia. जितना ये मोटा होगा steel bar, उतना वो tensile forces resist करेगा. तो the cross sectional dia is taking the tensile forces. So AST अगर इसका area है, area of cross section of all bars in tension, similarly for concrete, you have now the area of the cross section in concrete which is in compression. अगर ये width है इसकी B, and what is this? This is XU, neutral axis depth. तो compression में B into XU ये area will be in compression. B into XU will be in compression then. So area of concrete in compression is how much? B into XU, जो कि compression load ले रहा है. So what will be tensile force then? T will be stress in tension in steel bar into area of steel bar in tension. What is that? What is stress? 0.087 into Fy. Area क्या है? AST. I hope you are understanding this. If not, do tell me. What is C? Stress in compression in concrete into area of concrete in compression. I just told you this is 0.447 FCK. Stress जो अल्टीमेट स्ट्रेस है जो हम ले रहे हैं in which for the design purposes into area of concrete now is, I just told you, B into XU. Now for balance design, for a balanced design, T would be equal to C, that is 0.87 Fy into AST would be equal to 0.447 FCK into B into XU. Right? So for a balanced design means जितना टेंशन में फोर्स आ रहा है उतना ही कंप्रेशन में फोर्स आ रहा है. उसका ये मतलब है both will fail together at the same time, isn't it? Am I right? Are matching. So you would have now XU, you can get the XU, the neutral axis here from this equation. It would be 0.87 Fy AST divided by 0.447 FCK into B. So XU का ये value आपका आ जाएगा from this equation. Now what is XU? Neutral axis. So for a balanced section, you have got the neutral axis depth. The neutral axis depth is XU equal to 0.87 FYAST by 0.447 FCKB. You have now got this. Now, if you know FYAST, FCKB, अगर आपको ये चार चीजें पता है, then you can get the neutral axis कहाँ पर located है. So this you get from the balance section design approach, that you can first determine it's कहाँ पर neutral axis है एक section में, and this is very important to note down कि neutral axis कहाँ पर है, because all other designs are then based on this neutral axis. So if this is, I'll just finish within 5 minutes. If the total depth of this beam is D, capital D, तो हम क्या लेते हैं, up till the center of these steel bars, we take small d. This is known as, the capital D is known as overall depth of beam, and this small d would be known as effective depth. So effective depth. Now effective depth is, which is small d, is capital D minus cover, or the effective cover. Capital D being the overall depth and minus effective cover. So we can determine the neutral axis in terms of the effective depth. XU by D would be 0.87 FY AST